Hi everybody, thank you for having me. I'm looking forward to hearing what people think about what I have to say. So I think the original title I gave was something like Decision Making Under Severe Uncertainty, a Philosophical Perspective. And my original goal had been to try and present a sort of overview of a bunch of different topics that people talk about in philosophy when they're thinking about things like severe uncertainty. We heard a bunch of other names for it: deep uncertainty, ambiguity, Knightian uncertainty. Different people have different sort of names for this sort of idea. I changed my mind a little bit. I thought rather than give a broad but shallow sort of overview of a bunch of topics in philosophy, I thought it might be better to give you a narrower but perhaps a little deeper perspective about what actually happens when philosophers think about these kind of topics. So what I'm going to do instead is focus in on sort of one issue I've been working on recently, and present the arguments more as I would were I giving this sort of talk to a more philosophy-focused audience, and then there'll be various asides where I sort of tell you what I think's going on, and I hope this way you'll get some kind of idea about what it is that philosophers are doing when they're working on these issues. Okay. So the goal, just to set the stage, the goal I have is to basically suggest a new decision theory or a new modification of a decision theory for imprecise probabilities. And the hope is that this new modification perhaps not solve some of the problems, but at least mitigate some of the problems that IP, imprecise probabilities, have with decision making when the decision making happens in sequence, where you make a sequence of decisions. So I'll explain what I mean by these sort of things, what I mean by imprecise probabilities. I'll give you the core example of the sort of problem I want to solve. Yeah. My real goal, like I said, is not actually to do this, but to give you a perspective on how philosophers think about these topics, or at least how this philosopher thinks about these topics. So the plan, just to give you the overview, I'll give you a very short introduction to IP, to imprecise probabilities. As I understand it, I mean, this is a big topic that lots of people from different traditions work on. You know, there's work in economics that was mentioned this morning. There's work in statistics. People in psychology use this. So we're not all going to agree about what we're doing, but I'll give you my take on what IP means. Then I'll talk about this decision problem that I'm calling the Hammond-Algar decision problem. And then in the third section, we'll sort of go off on a tangent a little bit. And then hopefully by the time we finished this tangential look at topics like incommensurability and sequences of choices and the role of planning and commitment in decision making, I'll be ready to, at the very end, present the new suggestion for decision making. So I've been told it's conventional to start at the beginning. So I'm going to start by talking about a very short introduction to imprecise probabilities. So just to sort of fix some terminology, here's what I mean by the various symbols I'm using, right? There's some sort of state space which characterizes the ways the world could be, if you like, and then there are some sort of propositions, sets of states, which are, you know, things like, there might be various sort of, it might be, you know, there's a state where it's raining heavily and a state where it's raining lightly, and a state where it's not raining, and then there could be a proposition, it's raining, which would consist of the states. It's raining lightly and it's raining heavily. We have probability functions, which I'm going to indicate with the little lowercase p. So those are over, they're functions over you know, an algebra on the set of states. And these are supposed to represent degrees of belief. So most of the time I'm going to be talking about subjective probabilities this morning, we heard about imprecise objective probabilities, but if that difference makes a difference, I'm talking about subjective probabilities. Then we have the objects of choice, the things you're interested in choosing among. We could call them acts, we could call them gambles, we could call them lotteries, choose whatever terminology you like. And for the purposes of this talk, I'm just going to assume that those are functions from the state to real numbers. I'm just going to treat these as precise utilities. Okay, so I'm sweeping under the table a whole bunch of interesting and difficult topics to do with, there might be uncertainty about how good a particular consequence of an act is, for example. I'm going to sweep under the carpet any sort of concerns about risk aversion or anything like that. We're just going to assume that these acts determine some utilities, and the interesting structure that we're going to be looking at, the difficulty is going to come from how we get from our uncertainty about the states to the expected utilities. Okay, so the utilities I'm just going to pretend are super easy for the purposes of this talk, and the difficulty will come from the probability. So the expectation is just the probability weighted sum of the utilities in the states. Okay, that's all fairly basic. I hope none of that was too surprising to anyone. And we can talk about how we ought to choose in this kind of simple decision framework. The natural way to talk in this precise framework is to talk about maximizing expectation, right? So a choice function, so this is a capital phi and this is a small phi. They don't look different enough, annoyingly. I noticed that yesterday, but I didn't have time to research a new font so that had more different looking symbols. So this choice function is going to be a function that sort of takes a set of acts, the acts you're contemplating, and it returns the set of acts that you take to be choice-worthy, the set of acts that you think are good. Okay. And the standard sort of choice function in the precise framework will be to say you take the set of acts that maximize expected value. Okay, standard sort of maximization of expected utility sort of hypothesis. So that's the basics of the precise case. Why might we want to go beyond this precise case? Well, we saw some really good reasons this morning about why taking a single probability distribution and basing all of your decisions on that single probability distribution might be sort of difficult or problematic or unreasonable. I'm going to present some perhaps less convincing reasons to do this, but just these are the reasons that philosophers often appeal to. And we will sort of talk about these examples a bit later, so it's worth just having them on the table. So one classic example of deep uncertainty or ambiguity, a very toy example, a very simple example is the Ellsberg type cases. So the setup is you have an urn that contains some marbles. Some of the marbles are red, 30 of them are red, there's 90 marbles in total. And you've got the remainder of the marbles. You don't know how many of them are blue, and you don't know how many of them are yellow. That's the basic setup. And the intuitions you're supposed to have about this case is that, well, the probability of red should be 1/3, okay? But what sort of attitude should you take to blue or yellow? Well, here are some things that it seems reasonable to say. It would be odd to have different attitudes to yellow or blue, right? You're in precisely the same sort of situation with respect to yellow as you are with respect to blue, right? You know nothing about you know exactly the same things about how many yellow or blue marbles there are, precisely, nothing. There's somewhere between 0 and 60, that's all you know. And it seems like there's a difference in your attitude between how likely you think it is that a red marble will be drawn and how likely you think it is that a blue marble will be drawn, right? You know something about the chances of red, and that seems to inform your rational degrees of belief. You don't know anything about the chance of blue, or you know very little about the chance of blue, and it seems like that should inform your attitudes, right? And it seems to make a difference to decision making. So, for example, I'm going to offer you the choice between bet 1 and bet 2. Bet 1 wins when wins you a dollar or whatever when a red marble is drawn. Bet 2 wins you a dollar when a blue marble is drawn. Okay. Or I could offer you a choice between bet 3 and bet 4. Bet 3 wins you a dollar when a not blue marble is drawn, when a red or yellow marble is drawn, right? And bet 4 wins you a dollar when a not red marble is drawn. Okay. Now, it seems not irrational, it seems at least reasonable that you could prefer the bets where you sort of, you know the chance of the good outcomes, okay? So bets 1 and 4. So you know that there's a chance of a third that you'll win in bet 1. You don't know what the chance of winning is in bet 2, if you like. You'll know that the chance of winning in bet 4 is 2/3, right? Because all of the blue and yellow marbles together are 2/3 of the marbles in the urn. Whereas in bet 3 here, it's, again, there's ambiguity with respect to how good that bet is, and it seems like you might want to avoid ambiguity. Okay, it's difficult to sort of capture this idea in a precise probabilistic framework. So what should you do instead? Well, look, here's one probability distribution you might have, right? Just a third each, okay? But it's consistent with the information you have that, this distribution is possible, right? It's also, all of the non-red marbles are yellow. It's also consistent with the information you have that all the non-red marbles are blue, and anything in between, right? You have some sort of intermediate, you could have some sort of intermediate attitude as well. So the basic idea of the sort of imprecise probability approach, as I understand it, the sets of probability approaches, you take the set of all of those probability distributions, and that gives you an object that's kind of representing or characterizing your rational degrees of belief. So we've captured the two sort of intuitions I said seemed reasonable about the Ellsberg case, right? Every distribution has a probability of a third for red, okay? So we could sort of colloquially say that P of red is, so capital P is of red is a third, but the probability, if you like, for blue or for yellow is spread out over the interval 0 to 2/3, okay? So we've got the probability of red is fixed and known, if you like, and then the probability of blue and the probability of yellow are different from the probability of red and the same as each other. And those are the sort of things that seemed we wanted to capture. So this is a set of functions, and this is some sort of, derived function, if you like. Okay, here's another very brief justification of why we might be interested in talking about sets of probabilities as a representation of our uncertainty. So if you're required to offer a price for a bunch of different bets on certain propositions, and you're asked to set a price such that you're willing to buy bets about that proposition at that price and sell bets about that proposition at that price, you'll be subject to a sure loss, right? You'll be open to a guaranteed loss unless the prices you offer are probabilistic, okay? So this is sometimes called the Dutch book theorem, but since I've been living in the Netherlands the last year, I feel like we should probably get rid of this, obviously racist label. So I'm just calling this the betting justification. But here's the thing. Why should your buying price and your selling price for a bet be the same if they're allowed to be different, as they are in real betting markets? If they're, different in the same way that the buying and selling prices of foreign exchanges, right? Buying foreign currencies, you can't get the same price to buy as to sell, right? If we allow those prices to be different, but we keep in place the rest of the sort of coherence conditions for buying and selling prices, then your buying prices are going to be lower probabilities, right? I'll explain what that means on the next slide. And your selling prices are going to be upper probabilities. Okay, so hang on. I want to talk about sets of probabilities. We're getting there, right? So a lower probability, basically, it looks like the same sort of thing as for the axioms of probability function, if you like, except that you have a greater than or equal here rather than an equals. Okay, so it's super additive. And then the upper probability is sub-additive, right? So less than or equals rather than a equals. And you also have some other sort of relationships between your upper and lower probabilities. Okay, so what does this betting justification for upper and lower probabilities have to do with sets of probabilities? Well, they are very closely related to each other, and this is why it's worth looking at sets of probabilities. So for every set of probabilities, you can define a lower probability by basically taking the lowest value assigned to a proposition by members of that set of probabilities, right? The function thus defined is a lower probability in the sense of the last slide, and not quite the converse, but for every lower probability, you can define a set of probabilities which is such that it's non-empty. Okay, so there is a set of probabilities that kind of corresponds to each lower probability. This is not, if you look at this carefully, this is not a sort of one-to-one relationship, but we're going to gloss over those details for now. So you can have a betting justification for lower and upper probabilities, which is very similar to the betting justification for standard probabilities, and that's very tightly connected to sets of probabilities. So now we're going to talk about sets of probabilities. So here's again, just a few more sort of fixing terminology things. We've got a set of functions, set of probability functions. We've got various sorts of summary functions we can define. We can define a set-valued function that spits out the set of values assigned to a proposition by members of the set of probabilities. We've got the lower and upper probabilities that we defined on the last slide. We can produce imprecise expectations. Again, they're going to be set-valued, right? The set of expectations assigned to an act by probabilities in your set. Summary functions for the expectation as well. So now the question is, well, what sort of choice rule should we have? How should we make decisions in this kind of framework, right? We've got imprecise, what should play the analog role to maximize expected value? Okay, that's a big question. There's no consensus on how we should answer that question. Here are some candidates. You could seek to maximize minimum expectation. Okay, so this is not maximin in the sense of maximizing the minimum, outcome across the state. This is maximizing minimum expected value over probabilities in the set of probabilities. That's one choice rule you could look at. You could also do the following. So it seems like if you've got one act, psi, which always has which according to every probability function in your set has a higher expected value than phi, seems like there's something wrong with phi, right? It's expectation dominated, if you like. So it seems like those are not good acts to pick. So you should at least be choosing among the acts that are not expectation dominated. So maximality is basically the choice rule. Choose among acts that are not expectation dominated, right? Choose among the phi such that there's no psi which expectation dominates it. Okay, that's a very permissive decision rule, but there's another candidate decision rule, if you like. Another approach you could take is to basically pick a probability in your set and then do your standard maximization of expected utility with respect to that probability function. It's another approach you could take.
What do you mean by pick?
That's a very good question. So what do I mean by pick? That's open to debate, right? Somehow you select one. I mean, you could have some kind of principled, information minimization approach to picking a particular probability in your set, or you could just say, well, the important thing is you pick one and then act, to maximize expected value with respect to that, regardless of how you pick it. That sort of question of what we mean by pick isn't going to be so important in this talk. So maybe we can come back to that later if you still have questions about it. But you somehow select a probability function from your set and then act in the standard way to maximize expected value with respect to it. Okay, so what I'm going to do now is look at a problem that has been doing the rounds for a while now for imprecise probabilities, decision making with imprecise probabilities. So we've got some proposition H. I don't know what, I'm sort of uncertain about this proposition H. So the reason I'm calling this is basically what I'm calling the Hammond-Algar decision problem. So a version of this sort of problem was presented by Peter Hammond in the 80s as a problem for a certain sort of rule for decision making with imprecise probabilities. And then in a 2010 paper, it was rediscovered by Adam Algar and has since sort of generated a lot of interest. And I think it's worth emphasizing that this wasn't new to Algar, so that's just me being curmudgeonly and calling it the Hammond-Algar decision problem. So here's a version of this sort of problem. You got this proposition H. You don't know anything about. It's a proposition that you have severe uncertainty, very deep uncertainty about. Let's just say that the probability for H ranges all across the unit interval. I tell you up front, I'm going to offer you two bets on this proposition. So first, I'm going to offer you bet A, and then when you've told me whether or not you accept bet A, I'm going to offer you bet B. Okay? And basically, they're kind of mirror images of each other, if you like. So bet A wins, or bet A loses $10 if H is true, but it wins $15 if H is false. Conversely, bet B wins $15 if H is true, but you lose $10 if H is false. Okay? So the idea is if you think H is very likely, you'll want to accept bet B but not bet A. If you think H is very unlikely, you'll want to accept bet A but not bet B. And if you have some sort of middling degree of belief in H, you probably want to accept both bets. Okay? But the point is, whatever you think about the proposition H, it seems like it would be a mistake to refuse both bets. Okay? Because if you accept both bets, you make a sure $5. Whether or not H is true, you win $5. Okay? Because you win 15 on one of the bets and you lose 10 on the other. So whatever happens, you win $5. Whereas if you refuse both bets, you make no money. You get 0. So so if a decision rule tells you you should refuse both bets, that seems to be a problem with the decision rule. Okay? Let's be clear that this is a sequential decision problem. Okay? So if you think of it as just a one-shot, choose among the four options, choose among the pairs of options, there's no problem, right? Because Maximin says, well, this has a sure win of $5, so an expected value of $5. The expectation for accepting bet A but not bet B ranges over -10, 15, right? Likewise for refusing bet A and accepting bet B, and then refusing both bets has 0. So in a choice between these four options, this has the highest minimum expected value, so the Maximin choice is to take both of these. Refusing both bets is expectation dominated by taking both bets, so that option is ruled out by maximality. These three are still within the maximality choice set, if you like. Likewise for the identification theory, depending on what probability you pick, right, you might end up going for AB, you might end up accepting A and refusing B if you thought H was very unlikely, for example. But whatever probability you end up with, you're not going to do this one. So the problem is when you think of this as a sequence of choices, okay? So let's go through a sort of naive maxi-minor, right? I've got a choice between taking bet A and refusing bet A. Well, taking bet A has the range of expectations -10 to 15. Refusing the bet has expected value 0 in all cases, so you should refuse it. You do the same reasoning for bet B, you come to the conclusion that you should refuse both bets. So that seems like that's a bad decision rule. Now you may be thinking, wait a minute, hold that thought, because there's a reason why I'm calling this naive maximin. Maximality, likewise, at least makes it permissible, right? It says, well, in a choice between bet A and refusing bet A, right, neither option expectation dominates the other, so both are permissible. Likewise, in a choice between bet B and refusing both bets, both options are permissible. So it seems like we should, it should be permissible to refuse both bets, right? And all of the other options are also permissible as well. So again, that seems like a problem. So this, what we're doing is we're using whether or not it makes refusing both bets permissible as a way of ruling out candidate decision theories, okay? So even in the sequential choice, the sort of identification approach seems to work, right? You pick a probability, and then if the probability has H very unlikely, so if the probability of H is low, you're going to pick bet A and then refuse bet B, right? Because A is going to have a high expected value and bet B is going to have a low expected value. If you've picked a probability with a middling probability for H, you're going to end up accepting both bets, okay? But the point is there's no probability function which ends up choosing 0, or ends up choosing refusing both bets, okay? The important thing to note here is that the way that works is you pick a probability at the beginning and then you use it to make both choices. If you're allowed to switch which probability you choose, you identify with, if you like, once you've made your first choice, you could end up refusing both bets, right? Because you could have picked a probability that has a high probability for H, and so you, whichever way means you refuse bet A, yeah. So a high probability for H, you get here, and then you change what probability you identify with, and you end up identifying with a probability that has a low probability for H, and then you refuse. So the point is that the identification theory works by sort of making sure you stick to the same probability throughout the choice. Okay. But you can be a sophisticated maximin chooser, if you like, and basically work through backwards induction, okay? So you look at this tree and you say, okay, if I were to end up at the up node, right, this has a higher minimum expected value than, so choosing to accept bet B, having accepted bet A, has a higher minimum expected value than refusing bet B, having accepted bet A, okay? So if I were to end up at node A, or end up at node up, I would choose to accept bet B and end up with 5, right? If I were at node down, I would choose to refuse the second bet rather than accept bet B, okay? Because this has a higher minimum expected value. Okay, so what should I do here, given what I know about what I do at the future nodes? Well, so I know if I end up at node up, I will choose in such a way to give me $5 for sure, right? If I end up at node down, I will choose in such a way as to give me $0 for sure. I prefer $5 to $0, so at the initial node, I should choose up so that I know how I'm going to choose in the future. So you can be a sophisticated maximinner, and you can get around this sort of problem. Okay, so we saw sort of 4 approaches to decision making with imprecise probabilities. 2 of them seemed to fail in the sense that they didn't make refusing both bets impermissible, and 2 of them seemed to be successful. They successfully avoided making refusing both bets permissible. So what I don't really have time to talk you through today is the reasons why the 2 decision rules that were successful in this case are problematic or unsuccessful for other reasons. We can talk about that in the Q&A if you're interested. But just to give you an idea, in the interest of time, I'm just going to skip that point. So the identification theory, it doesn't allow you to rationalize this sort of ambiguity aversion, the Ellsberg marbles in urns case, right? Because if you identify with a particular probability, you can't have the ambiguity averse preferences in the Ellsberg case. And the sophisticated maximin approach in other sort of decision problems, it has this weird feature that someone choosing by this sophisticated maximin approach will pay to avoid learning information, information that doesn't sort of harm them in any way. And that seems like a strange consequence, right? It seems like free information, you should just accept that because it can't make you worse off. So we're stuck. We need another approach to decision making with imprecise probabilities. I want to spend the last, how long do I have left? 15 About 15 minutes, okay. So I want to spend the last 15 minutes basically going off on a couple of tangents before we come back to understanding a new sort of decision-making approach. So I want to diagnose the problem with this. What's going on in this sort of case is basically you have choices. You end up making choices between options that you find incomparable, right? You don't have a preference between an expectation of 5 for sure and an expectation ranging between -10 and 15, right? Those are just sort of difficult to compare, if you like. And making sequences of choices between options that you find incomparable is difficult anyway, right? So we're now going to look at an example of this sort of incomparability, this incommensurability. It doesn't have anything to do with imprecise probabilities, right? It's just going to be incommensurable goods that you just can't compare, and see that we have exactly the same kind of problem. And we'll look at what we can do to solve that problem, and then we'll apply that to the case of imprecise probabilities. Okay, so you have 2 choices, right? You're going to choose between a scuba diving holiday and a safari holiday. And these are both really great, but you can't compare them. You can't, these are just 2 different kinds of goodness that you can't really compare to each other. Okay? But you're offered this holiday in a slightly strange way. Okay? So box A contains the ticket for the scuba diving trip, and box B contains the ticket for the safari trip. Okay? Now, before you get to choose whether you take box A or box B, you're going to have a choice to put some amount of money, right? Some, let's say $50 spending money into one of the boxes. Okay? And here's how it works. just so we're super clear, right, this is, again, it's going to be a sequential decision problem, right? You choose which box to put the money in, okay? And once you've made that choice, once the money's in the box, you choose between the boxes, okay? Now, let's say by stipulation that that $50 is not enough to sweeten the deal so that one holiday becomes obviously better than the other, okay? So you prefer box A with the money to box A, obviously, right? Because money has let's just stipulate that this is someone who prefers more money to less. But you prefer box B with the money to box B for the same reason, okay? But let's stipulate that no other preferences hold between these options, right? So you have you can't compare A to B, you can't compare A to B plus the money, you can't compare A plus to B, and you can't compare A plus to B plus, okay? So let's make this a sequential decision problem and then work through it, right? And let's do it by backwards induction in the same way that we did before, right? If I were to end up at node 1, I would have no preference between these options, right? By stipulation, I have no preference between the Scuba holiday plus the money and the Safari holiday, okay? I have no preference between those two options. Likewise, if I were to end up at node 2, I have no preference between the Scuba holiday and the Safari holiday plus the money, okay? So how should I choose at the initial node? Well, I know that whichever node I end up at, I won't have a strong preference for one of the options versus the other, okay? But hang on, right? It seems like you should choose whatever box you put the money in, right? It seems crazy that you can't have the preference to put the money in the Scuba box and then take the Scuba box, right? It seems like making this a sequential decision, something has kind of gone a little bit wrong, because even though you have no preference between the options at node 1, there still seems to be a reason why you shouldn't choose the Safari holiday once you've put the money in the Scuba box, okay? So what is going on in this sort of sequential decision problem? What can we do to fix it? So one suggestion that has been made is that...
Wasn't that a stipulation that your only preferences was between A plus over A plus over? So it was stipulated. You could have stipulated something else. But your stipulation was that you have no preference between those two pairs.
Yeah. So I've stipulated that you have no preference between these pairs. Right. But it still seems like if you're here and you're choosing where to put the money, right? If you put the money in one box and then take the other box, you could have put the money in the box you end up taking and end up with something you strictly prefer.
That's what I'm suggesting.
I mean, maybe we can come back to this later. Thanks. I'm kind of less interested in the details of this example. I want to sort of draw a moral from this example and then apply it to the imprecise probabilities case. So if you have the same kind of worry in that case, then maybe we can talk about that in the question period. So one suggestion is that what should happen in these sort of cases is we should make a plan, make some sort of commitment, and then stick to that commitment. Okay. And that should sort of override our lack of preference here. Okay. So, and I think that's broadly right, but I think it's broadly right, I think that's right in this case, but I don't think that's the right case in general. And I want to give you an example of where this sort of planning approach to sequential decision making seems wrong, and then I'll diagnose why that's wrong. And we'll come back to the examples at the end. So here's another example, okay? Again, I'm using a bunch of sort of very toy examples, right? Not because I think that these are inherently interesting or anything, but I think if we can, in the same way you use toy models in the sciences to explore specific details of a particular sort of dynamics or whatever, I think we can use toy decision problems to learn something about the decision problems we're actually interested in, which are decision problems in the real world. So let's imagine that you're at a party, you have to teach tomorrow, you want to have a glass of wine, but if you have one more glass of wine, you'll want to have another and another, right? So you think because of that, maybe don't have the glass of wine. But, well, what if you could make a plan to just have the one glass of wine and then stop? It seems like that sort of plan would just be ineffective, okay? So here's the temptation problem as a decision tree, right? Let's imagine that if you get to this node, you'll prefer to have another glass of wine. Whereas when you're here, right, your preferences at the initial node, if you like, are to have the glass of wine and then stop, right? But thinking about it in the sort of backwards induction way that we were thinking about before, given it's almost like think of your future self as another player in a game, right? This other player, your future self's preferences are for more wine rather than stopping after the one glass. Given that, that your move should be to have a glass of water rather than give your future self this opportunity to defect, if you like. It seems like if this is what about what your preferences will be after the glass of wine, your planning or your committing to only having the one glass of wine isn't going to be effective, or there are at least cases where the planning or commitment doesn't have this property of overriding your future preferences or your preferences at the next moment in time. So I wanted to, I have a little bit more to say about the sort of planning and why this can't be a good general approach to decision making, but in the interest of time, maybe I'll just sort of skip over this. So what I want to sort of point out is that there's an important difference between the Scuba Safari case and the wine case, right? Both are cases where you appear to have a preference at the initial node, if you like, that then you almost stop having at a later node, okay? So from the initial node, it seems so from the initial node, you don't want to have more than the one glass of wine. But once you get to that node, your preference is reversed, and you do want the more wine. And in the Scuba Safari case, you have at the initial node, it seems like the option to take the box that doesn't have the money in, whichever way you put the money in the boxes, that seems like you could have done better, right, by taking the box with the money in. But in that case, it's not the case that your preference reverses. It's not the case that you have a preference, you have a strict preference for less wine rather than more, which then reverses once you've had the glass of wine. You have a preference to take whichever box you put the money in, which sort of evaporates when it's a choice between the incommensurable goods in the second node. And I think that's an important difference. So the point is, if you just have this, thanks, I probably won't need 5 minutes. But so in the Scuba or Safari case, right, what happens is here you think, well, it would be odd of me to go up and then choose the Safari, and it would be odd to go down, i.e. put the money in the Safari box and then choose the Scuba holiday. But once you get to, let's say, node 1, right, you have no preference between these. But it seems like you can still sort of satisfy your ex ante preference, your initial preference, right? Because it's still compatible with your preferences to choose the box with the money in. Whereas in the wine case, it's no longer compatible with your preferences after having the glass of wine to do the thing that you originally preferred. Okay, so I think that's an important restriction on the scope of this sort of use of this idea of planning or deferring to your ex ante preferences. So basically, here's my proposal for a new imprecise decision theory, or a modification of an imprecise decision theory. Use that maximality rule, so choose among the things that are expectation or not expectation dominated. And then, when you have a whole bunch of options that are not expectation dominated, you can use, preferences you had in the past that you no longer have, if you like, to break ties among the options. The last thing I'll do is just show you how that works in this sort of case. From the initial node, okay, you know that this is not a good option because it's expectation dominated by something up here. Okay. But you have no preference between going up or going down. Those are sort of incommensurable in terms of their expectations. So let's imagine that you end up going down, right? That's permissible, it's consistent with your choices, it's consistent with your expectations, if you like. Once you're here, right, neither of these options, neither of the options that are available to you, expectation dominate each other. Okay, so maximality has both of these options in the set of permissible options, if you like. But you can now defer to what you thought in the past, what you thought back here, that this was a bad option because it's dominated by something that's no longer feasible for you, right? You can no longer get up to that part of the choice tree. But that can still sort of break the tie and make you choose this option rather than that option. Okay, so that might be part of a theory of rational decision making. Or maybe this is just part of a theory of reasonable decision making. That's a distinction I quite like and one I might make more of in the future. But in any case, I think we can use this this sort of tie-breaking approach to get a decision rule that this maximality decision rule sort of doesn't have the problems that the identification approach does or the sophisticated maximin approach does. But it had the problem with this decision problem. But we add this sort of tiebreaker decision rule, and we get a decision theory that doesn't have that problem. So that's what I wanted to tell you about today. So thank you for your attention.
So Marcus Pivato, University of Cergy-Pontoise. So this is an interesting suggestion, but maybe I misunderstood it, so you can correct me if I've got the wrong idea here. In this particular example, you basically could go up or down at the beginning, but then once you go down, you'd go to NB because you recognize that sort of in a counterfactual sense, NN is still dominated by this option AB, which is not available anymore, right? So there's sort of two issues I would have with that. One is that if I know that I'm going to do that, I can anticipate how my future self is going to act. Then at the initial node, when I choose down, I'm effectively choosing NB. Like I know this is how the story is going to end already. Kind of like when I choose the first glass of wine, I know my future self is going to have 4 more glasses of wine.
Yeah.
So in that case, it's not really the case that you're sort of freely choosing down and then you're going to sort of sort it out later on. You're basically choosing NB. So then at that point, in the initial node, you have to ask yourself, what is a good reason for choosing NB? And at the initial node, you have no particularly good reason to choose NB. So you've sort of pushed the problem back one stage. If you assume that you're going to be dynamically consistent, that your present self has to correctly anticipate your future self's choices, you haven't really solved the problem. You've just pushed it back. And my second question is kind of going in the other direction, which is that when I'm somewhere in the middle of a decision tree, like the past has already happened since the day I was born, since, I don't know, humans came down from trees. Now I'm at a certain node in this decision tree, and I'm thinking about what I should do in the future, and I start considering my present options to these sort of counterfactual things which could have been available if I'd made different choices in the past. How far back in time am I supposed to go? Am I supposed to go back and think about what would have happened if when I was 15 I'd asked that girl out, blah, blah. Exactly. So the point is that there has to be some kind of a limit to the sort of this counterfactual exploration of the no longer available branches in the decision tree.
Yeah, good, thank you. So the first question first, yeah, you still have no good reason to choose NB in the sense that, it's equally permissible for you to choose AB or to choose AN. But the point is, there's some reason not to choose NN, right? That's sort of all I want out of this approach. It's true. Yeah, this is maybe the right way to think of this is, you sort of have this decision tree in mind when you're deliberating, and then ultimately you cut off that NN branch because you anticipate your future self's choices correctly. And yeah, you still have no reason to choose NB rather than AN. But this is the point, right? We're in a framework where, because you're so uncertain about the propositions, it might be that you don't have good reasons to choose one option over the other. But the point is, there are still some options that are bad, and we want to at least rule them out. Okay, and that's enough for me in this context. In that sense, I'm interested in what constraints does rationality put on your decision making, rather than what's a reasonable way to make a decision. And I think maybe this is I think maybe this is part of rational decision making, and then it may be that you have other things would give you some reason that isn't sort of a constraint of rationality, but some kind of reason to choose one of the options over the other. But that's a separate project, if you like. The other thing to say is, yeah, I take your point that how far back do we want to keep these counterfactuals, if you like, in mind. Maybe you want to go sort of far back enough that it helps you determine what choices to make, right? In the sense that the goal here is to think about, and this is maybe more about sort of reasonable decision making rather than rational decision making now, but if you're faced with a decision problem and you think, oh, I don't have any sort of preferences between these options or something like that, but past me would have done this rather than that, maybe that's sufficient to break the tie. And if what you want to do is determine a decision in a way that's better than guessing, then maybe that's sufficient, right? And if
in some sense, you could propose your method as kind of a lexicographical one. Then the idea is you'd only employ this counterfactual reasoning as a second order consideration when you're just totally indifferent otherwise.
Maybe, yeah.
Okay.